Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
And your co-host, Rich Gear, here as well. But I'm going to tell you, Doug, the nature of the chemical bond. This is Doug's bailiwick. I'm going to be just the sideshow here.
Well, you can ask questions.
I'll ask questions if I can think of them.
This is really for you, Rich, because you got this started in me because we got talking a little bit about leaching and radioisotope dating, and that was that's one of the things that makes this whole topic of the nature of the chemical bond important to creationists. And the other thing is understanding bonding in life molecules like proteins and DNA and RNA. Okay. This has a lot to do with it. And I can remember in high school, it was many years ago, I picked up a book in the high school library by Linus Pauling, and it's called The Nature of the Chemical Bond. Oh. And that is the results of what I'm going to be talking about here, is that we're going to talk about a little bit about chemistry, and it was one of the reasons why I thought of becoming a chemist when I was in high school, and that's what I ended up for at least three of my years in chemistry in the college. And
so hopefully this is going to be not off-putting for those people like me who are not chemical or chemists or chemical engineers or any of that stuff. You know?
I'm going to try to make it interesting, but I'm going to break it down a little bit so that you can understand what is really going on.
Well, that's the first part. That's, to me, important to get what's going on here.
And so I wish that I had brought up the periodic table, because that really would help us a little bit, but I will put this in the periodic table in the background so that we can take a look at that very quickly. And I want you to understand a little bit of difference between the radioactive stuff, which is where you have the actual nucleus of a element breaking down, versus what happens with the electrons in an element. So
radioactive means that it's unstable. Is that what it means?
The nucleus is unstable, and it breaks down into something else.
Something else. So what's the other one? So it's not radioactive. What is it? Inert, or what is it? Is it called anything, or just a?
Yeah, it's stable. We would
stable.
Call it
okay, stable. Okay. Stable. So radioactive and stable. Because everybody has heard the term radioactive, uranium, and plutonium and things like that. Right. But that's what makes them radioactive, is their nucleus, which is the center part of an atom, right?
The nucleus is the center part of the atom, and it's made up of protons and neutrons.
And the protons can leach off or break down or lose or gain, or is that what it is?
Yeah, you can either split the atom, like what happens with uranium, or it'll emit an alpha particle and it'll change to some other element. That's what they measure when they're doing radioisotope dating, is they measure the parent element to the daughter element. Okay. And so you have the two different elements. Now, what happens in the chemistry is that you have stuff going on with the electrons. And that's what I was going to talk about tonight a little bit, is each element, you have the electrons orbiting around the nucleus of the atom.
Yeah, that we remember.
And orbits are kind of interesting in that you have the orbitals are called s orbitals, p orbitals, d orbitals, and f orbitals.
So there's four kinds.
Four different kinds.
And they're increasingly more complicated, right?
Right. The s orbitals is actually spherical in nature, and if you take a look at the left hand of the chart of the periodic table, you have the elements that have the s orbital, as the primary orbital that's exposed. Now, what you have is actually you have what they call shells. The shells are the inner orbitals, and then you have the higher energy orbitals that orbit around them. And as the atom gets bigger, it increases in size. No, they don't necessarily increase in size, but as you go up the periodic chart to the larger atoms, with the heavier atoms.
They have more electrons?
They have more electrons, and they have more shells. And so there's a 1s, a 2s, and a 3s orbitals. You have the 1p, 2p, and 3p orbitals. Then you have the 1d, 2d, and 3d orbitals, and then 1d, 1f, 2f, and 3f orbitals.
So all of them have 3 versions of?
Yeah, and you could probably go higher, as you go higher in the chemical, in the number of elements, the more unstable they become, and so they don't like to get so big. In fact, it's kind of a real problem in taking a look at the evolution of these elements, is to try to figure out how those elements could have come about, because if you start out with hydrogen and try to make more and more and more complex elements, you have to invent some physics in order to do that.
Yeah, to me that's the thing. This on a God level for me is like the Lord Himself could make from the simplest element, which He would even create Himself out of nothing, and increase that to make the old what are they, alchemists, where they make lead into gold, or they make, in this case, hydrogen into gold, or if you will, hydrogen into everything we see in the universe. You know what I'm saying? I don't know if that's an apt analogy or not. I may be getting a far field, but it just seems to me the power needed to do something like that would be so unbelievably awesome and incredibly, it'd be terrible to behold if you think of it, if we get, in our own physical bodies. But so that is so I guess what I'm getting is, why do the orbitals change into these weird looking, like the S ones you say are mainly spherical, but then what are, let's say, what's the next one, D or
no, the next one is P.
P,
I'll show you the P orbitals. These are the P orbitals, and they're in 3 dimensions. You have the X, Y, and Z axis of how this works. And so
do they orbit around the nucleus in different patterns or something? Is that what
what they are is really standing waves. And a standing.
You're going to make this less complicated. I'm telling you. Okay, go ahead. Go for it.
Well, and it's all part of an equation called the Schrodinger Equation. And this is the thing that when Mike Nolan was here, his eyes glaze over, my eyes glaze over, and I take a look at this math and I wonder how does this guy figure this out?
How did he figure it out?
But what it does is it describes in 3 dimensions what these orbitals look like. Now, the d-mode of orbitals look even more complicated. They look like this. But when you get to the f orbital, that's where it really gets complicated, and it looks like this.
Well, that is funky.
And so these, and what happens is that if anything moves in a straight line, it has a waveform to it. Even if you pitch a ball down the at a batter.
From pitcher to catcher, okay.
At the angstrom level, which is way down the submicroscopic level, you have a waveform that is following.
And the wave is made up of, what is it?
Well, it's how it wiggles as it goes down the path.
Through the path, okay.
But in this case, what you have is that it's orbiting around something, and so it's creating this wave pattern that's like a figure 8. Because it's trying to do the wave at the same time as it's doing the orbit.
Okay.
And so it's affected by the gravity of the nucleus.
So does that work with all the S to the P to the D or whatever?
Right, and that waveform is what's defined by that Schrodinger equation. And so that's about as complicated as I want to make this. Okay.
Okay, good.
So what I wanted to talk about is what happens with ionic bonds. Now, you have on the left-hand side of the periodic table some elements. You have at the top lithium. Well, actually, at the top is hydrogen.
I was going to say, it was hydrogen, okay.
Hydrogen's at the top, then you have lithium underneath it. Over on the other side, is the noble gas helium. Now what you have is that the s orbital only has 2 electrons in it. And those are the spherical elements. I mean, it's the spherical shells, so to speak. And so in the case of hydrogen, it's very reactive. It likes to give up or actually acquire another electron.
So hydrogen wants to grab something.
The hydrogen wants to either give up or acquire something.
Or gets either way.
Because either way, what it does, it just becomes like a noble gas. The noble gas doesn't want to react.
So hydrogen is unstable?
Hydrogen is, the nucleus is stable, but the element itself wants to react because it wants to either give up or acquire an electron.
Okay. So that's why hydrogen works well like with the H2O, like oxygen.
Right.
Is oxygen, but you got 2 hydrogen atoms to 1, right? 2 hydrogen to 1 oxygen, right?
Yeah, 2 hydrogens to 1 oxygen. Here's a picture of that.
And that makes, you think about, okay, because oxygen, is that an unstable element?
Well, it is a reactive element.
It's reactive. You have 2 reactive elements, and they come together to make one of the most stable things in the universe, water.
Right, and water's, you can write 500-page textbooks on the chemistry of water.
I believe it, because water is amazing to me. Everything about water is
I found
amazing.
my periodic table, so we can talk
there you
about
go.
that. So, but here, the chemistry of water is very fascinating because the 2 hydrogens bond on one side of the oxygen. And what it does, it's doing a covalent bond where it's sharing electrons with the oxygen. Now, there's 2 different kinds of bonds that are most common. One is the Ionic Bond, and that's where the other element, the element on the left-hand side of the periodic table is the ones that wants to grab electrons. And these over here,
they grab them from over here?
Yeah, they grab them from over here. The ones over here are the ones that want to give up the electrons. And the further they are on one side, is the more reactive that they are, the more likely they are. Because, like over here, you have these are what's called the alkali metals, and they're the ones who only have 1 electron hanging out there. And that means that this chlorine over here will want to grab that electron, and now the chlorine becomes stable, and so does the sodium. The sodium is one of the...
That becomes salt?
It becomes salt. And that ionic bond, they're attracted to each other because they're positive and negative.
So now why is all of this really important for creationists to understand it? I mean, or are we to that point where we want to get to that? I mean,
let's, because that's enough for us to understand the ionic bond. You have, there's 2 elements that are, this would be affected by this in the radioisotope dating. That's rubidium and strontium. They're sitting over here, right next to each other. And when you have a radioactive decay, the parent element and the daughter element are usually right next to each other, or actually 1 or 2 down.
so uranium and lead are next to each other?
Yeah. And I'll show you where that is next.
And potassium and argon are next to each other?
Right. Potassium's over here, argon's over here, but they're actually only one element away. Argon is 18 and the potassium is 19.
Okay.
And so they're very close. And so what happens with rubidium is that it loses, it actually gains a nuclear element and then becomes strontium.
Okay, so that's what we're talking about, parent and daughter, in case you haven't.
Right.
Parent is the original element, which is radioactive, which is unstable.
Right.
And it wants to give up something, or probably give up something mostly, right?
Right.
And then the daughter element is what it turns into by doing that. Okay, so that's that, and it's like it starts out with uranium, and down the road it becomes lead, and rubidium becomes strontium.
Right.
Potassium becomes argon. And what's the other ones? I don't know. There's other ones, but anyway.
I'll show you the other ones later.
Okay.
Well, let's talk about rubidium strontium because that's the easiest to understand. Rubidium will has one electron sitting out there waiting for the chlorine to grab it. And so you have rubidium chloride will become stable and it dissolves in water. And what happens with this oxygen, with this water, is that it forms these hydrogen bonds, and it will want to dissolve anything that's ionic of this nature. And the rubidium salt will easily dissolve in water. But strontium chloride, you have 2 electrons over here. And then you have to have 2 chlorines that will bond to it. So you have SrCl2, which is strontium chloride in this case. And those bonds are hard, ionic bonds are harder to break because you're borrowing 2 electrons over here. And when they glom together, the bond is much tighter.
Okay.
And so those salts will precipitate out faster than the rubidium salts. So what you have is that if you have a situation where there's like a flood or something like that, where you have a lot of water.
Okay, I was going to get to that, yeah.
You're going to have a differential in the way that those 2 elements are leached out of a sample because...
so you're saying if we have a flood, that might give us a bad reading as far as decay rates because of leaching, and the rubidium is less stable than the strontium. Is that what am I right there?
The ions, ions are stable in themselves, but they're more likely to separate.
That's what I mean. Okay, I guess that's what I meant.
They're more likely to separate into their ionic things than when you have them double bonded with the.
So you're likely after a flood to see more strontium than you will rubidium, is what you're saying.
That's
and that
correct.
will give you an older date.
Yeah, it depends on where that rubidium goes when it gets.
Of course, yeah. All right, okay.
Because that's the type of thing that might happen. So then you have potassium, which is one element up here. And that, of course, is again a very soluble in water element. You have argon. That's a little bit different because that's a noble gas. And that's already stable. It doesn't want to react with anything. I don't know if there's any argon compounds at all.
Okay.
Because now if you go down here a little bit lower, it's easier to perform covalent bonds with some of these, with krypton and xenon. I think there's like a xenon hexaoxide or something like that, or hexachloride, where it will form ionic bonds and borrow it because it can. But that's really unstable stuff.
It doesn't last long.
No, it doesn't last very long. And that's only because oxygen or chlorine are so reactive, it'll borrow electrons from anything.
Oh, okay.
But it won't do it with argon or neon that I know of. I've heard that there may be some argon compounds, but they're very rare. Sometimes what they'll do is they'll have what's called a Clathrate, and that's where you have an organic molecule that looks like a cage, so like a buckyball.
Okay.
And it captures an argon in the middle of it, but it doesn't bond to it, but it traps it.
Okay.
And so this little buckyball floats around and with that. And so
what is it? Okay. All right.
But anyway, if you go down here to uranium, let's go to the uranium-lead series. Uranium's sitting down here. This is an actinide metal, and uranium is very reactive. Not only with being radioisotope that decays, but if you have metallic uranium and you're turning it on the lathe, which they do in the atom bombs,
okay,
it'll catch on fire.
Really?
And so you have to be very careful with it, and they would preserve it. But the uranium decays down to lead. And now, these are the guys with F orbitals. And so this is a little bit more complicated, but you have uranium that decays to thorium, and then this part actually fits in between these two guys. And so what you have is that it's over here. Here's your lead. It decays. Thorium decays to polonium, and then it decays to lead. And leads are stable isotope.
Polonium, isn't that what the radiohalos are all about?
Exactly, yeah.
Okay.
And that's an interesting thing, is that the radiohalos are burn marks in different samples where you can see that it actually existed. And
back in the 70s, 80s, when was it Gentry?
Robert Gentry was talking about these, and there's polonium halos that are isolated where it didn't have any burn marks from the original uranium, which means that when this sample was formed, it was formed only with polonium.
And that's something which almost gives you like a smoking gun to show you that the dating methods are skewed because they assume that everything was 100% uranium at one time.
Right.
And this seems to be a smoke gun to tell you, no, there was actually things that were created pure polonium to start with, because he takes them out of the granites, doesn't he?
Granites,
which are from evolutionary standards, long Earth ages, deep time advocates. That's the basic rock. That's the bedrock. That's the initial rock. And as far as I know, Doug, they've never been able to duplicate the creation of granite in the laboratory. They've never been able to make rhyolite
or something.
Yeah, they've never been able to make granite. It's made, we believe, as a creationist, it was made by fiat, by God. And that would make sense. You'd see polonium, you'd see these radiohalos, because their half-life is, some of them like a few seconds, and some of them are even really even a lot shorter than that.
Well, what happens when the uranium decays, one of the areas that in the decay chain, it will give off a helium atom.
Okay.
And so the problem with that is that the helium will be captured in the sample, and so and what they've measured in the samples is that they've not only measured that there's way too much helium in the sample.
Oh, yeah.
Because it leaches, it escapes, and they've actually measured that escape rate out of the sample.
Oh, okay.
And so because they know that it can't be old. And so, that's a big problem for the evolutionists and their deep time radioisotope dating methods. And so that's a little bit about that. There's other ones. There's the lutetium, which is over here, and that's right next to the hafnium, which is over here. So this is 71 and 72.
Is that do they use that for radiometric dating?
Yeah, they do.
What's the half-life of that supposed to be?
Well, that's supposed to be in the millions of years.
They're all millions of years, okay.
But not all of them. You have carbon-14, which is
that's a different deal, though.
Yeah, you have which is decays from nitrogen. They decays into nitrogen 14. So, but the lutetium and hafnium, and then neodymium samarium.
Yeah, that's the other one. Neodymium samarium, yeah.
Yeah, I was looking at.
Because uranium is 4.5 billion years, isn't it? Isn't that is that the half-life? Is that a half-life? 4.5 billion years?
Yeah.
It's long.
Yeah.
Yeah.
So those are the different types of methods, but each of these are colored by their chemistry. The chemistry being how they react with water and the chemical compounds.
Do all of these react with water?
They do, yes. Each of these methods are ions that readily break down.
Does water leach off stuff from the parent element? Does it leach elements to get it closer to the daughter element? And does water do it for all of these, is what you're saying?
It would be more likely for it to leach out of the sample than it would be for it to leach into it.
That's what I was getting at, yeah.
But that's not the case for the potassium argon, because what you have with argon is that you have the possibility of argon leaching into it. Because, it isn't leaching, it'd be the original composition of the rock. Because when the rock was formed, it would be engulfing some of the atmospheric argon into the sample. And so you can't tell the atmospheric argon from the argon that would have come from
it seems like, Doug, is like we've talked about this in shows past, where all of these have issues. We've talked about the assumptions based on all radiometric dating, and there's lots of them. The assumption of how much parent element there was to daughter element at the beginning of when this was supposed to be done. We've talked about the idea that things could leach off. And we also talked about, obviously, the rate thing about are there things that can accelerate or speed up the decay rate, looking like speed up. But to me, the leaching shows the most problematic thing for the. That seemed like it would play havoc with all the dating mechanisms.
It would. Now, also to understand the hydrogen bond a little bit. What happens here when water is created, you have a couple of electrons sitting out here, which these are p orbitals, and so this is a little bit misleading because this looks like an s orbital, but it isn't. This is a p orbital, and so the p orbital sort of shoots out like this, and that's what causes the hydrogen bond, because this will bond to another water molecule, or it will bond to anything that's like it. And if you want to see the hydrogen bonds in action, you just pour on your Cheerios some milk, and then eat up most of the Cheerios, but leave about half a dozen floating in the milk, and you'll see the water tension move those Cheerios around so they sort of connect to each other.
No, I've never noticed that. Now I got to try that.
And so that's surface tension, and that's what these little water walker bugs will land on.
Yep.
And that's the hydrogen bond. And the hydrogen bond plays in the weak bonds of life. And also you have the action where you have a oily type of compound, like a that hates water, and so it'll sort of bend the proteins into a shape where all the oily stuff connects together, and all the things that like water sort of hangs out on the other side. And so it just helps in shaping the proteins, and that has meaning. It has all purpose, because it's those bonds that connect together everything, along with the ionic, the covalent, and the hydrogen bonds. The hydrophobic bonds will bend the proteins in the proper shape, and that's what causes them to have the enzymatic activity. Well, we hope you enjoyed our little tour of the chemistry of the chemical bond. And we'll see you next time on Revolution Against Evolution.
Bye now.